So this is an example of monoclonal antibody production utilizing CDM-HD. As I stated earlier, hybridomas was kind of the raison d'etre for the development of hollow fiber bioreactors in their first main application, and this is because of the biology behind monoclonal antibodies. So Cesar Milstein got the Nobel Prize in 1978 for his hybridoma technology, along with one of his co-workers. To make a hybridoma, you take a B cell and you fuse it with a cancer cell to immortalize it. But one of the ways that cancer cells locally immune suppress or inhibit the activity of B cells is to secrete TGF-beta. So Cesar Milstein knew that when he did this process that he was making a cell that inhibits its own growth. So B cells secrete cancer cells secrete TGF-beta. Its molecular weight's around 27,000 Daltons in its active form, and it will directly inhibit hybridoma growth and production. So hollow fiber utilizes its molecular weight cutoff, so we allow the TGF-beta to diffuse away and trap the antibody, 147,000 Daltons, trap the antibody in a small volume of the ECS. So hybridomas will grow faster than any in hollow fiber bioreactors than in any other type of system, and will also have much higher specific productivity when you can get rid of the TGF-beta. So any method that doesn't incorporate the removal of TGF-beta from the hybridoma culture is not taking advantage of the fundamental biology that's involved with hybridomas. In this particular case, this is Aaron Bromage at the University of Amherst, and he's part of the National Veterinary Diagnostics Antibodies Consortium. And this is just kind of a general example. I'll say this is above average data, but I do like to point out that this is not a purified product. This is simply a straight harvest. You take the cells and spin them down and then ran the gels. Now, admittedly, this is not the most sensitive of gels, but I think it's still pretty impressive when you can see that approximately, we'll say 85% of the protein that's present in the harvest is antibody product, which is some small molecular weight schmutz that we find down at the bottom of the gel. For his first hybridoma, he produced about 168 milligrams of antibody and 60 mils of harvest, average productivity at 2.8 milligrams per mil, consumed 9 liters of media in 3 weeks worth of cultures. The other antibodies pretty similar, 159 mgs and 70 mils volume, average concentration 2.3 mgs per mil, and consumed 11 liters of media in 3 weeks. Typically, our C2011 cartridge will consume a liter of media every 2 days. We like to harvest every other day. So we typically see a concentration of somewhere between 0.5 and 5 mgs per mil, and productivity of between 5 and 50 mgs of antibody every 2 days. Another issue with hollow fiber is that we can, in fact, utilize antibiotic-free culture system, and in this case, then we can have very low endotoxin. So if endotoxin burden is a concern, the small volume of the harvest can facilitate lower endotoxin, because endotoxin tends to be volume dependent and co-purify with antibodies sometimes. So the smaller the volume you have to deal with, the lower endotoxin burden that you'll have to clean up later. And we've produced over monoclonal antibody for over 6 months. In fact, the record is held by the Duke University Monoclonal Antibody Core Facility. They set up a cartridge in January of 1 year and then closed it down so they could go on Christmas break that following December. This is an example of a large recombinant protein produced in a CHO cell. That's an extremely large protein. It's 6 IgG1 subunits held together with 3 IgA tails. I call it a real Franken protein. And in this particular case, the top trace is the product that comes from the cells grown in flash culture. We take those exact same cells, seed them into the hollow fiber bioreactor, and we can see in the top trace about 40% of the protein is produced as an improperly folded monomeric subunit, and in the hollow fiber cartridge, 95% plus of the protein is expressed as a properly folded hexamer. So it's these improved cell culture conditions that result in uniform and complete post-translational modifications of a very complex and difficult to express protein in a mammalian expression system. So in this particular case, this is an image of the protein in question so we can see, and I'm always amazed to look at this for several reasons. First off, this is not a computerized drawing. This is an actual cryo-electron tomograph. When we can see 1, 2, 3, 4, 5, 6 IgG1 subunits held together with 3 IgA tails. And what Dr. James Arthos has done here is substituted the FB region of the antibody for CD4 receptor. So he's made a dodecaramized CD4 receptor, 12 CD4 receptors all in a big loop. And you can see here they're binding to GP120 on HIV. So this is a protein that was designed to cross-link HIV and activate it. And in fact, he produced 500 milligrams of protein in a volume of about 5 liters in a period of about 45 days using our system, and utilize this for animal research. The other thing about this slide that I find impressive and sometimes a little bit depressing is if I look at the date and I see it's the Journal of Biological Chemistry, September 2007. I remember being so excited when this came out, and now I look and I see it's 11 years ago, so I wonder where the time went. Here's an example of some raw harvest from a CHO cell line, and they did some interesting and a little bit different things with media change, but the fundamental thing to look at is on the left. We can see measurement of cell viability, and we can't see it directly, but I can tell you here the cells are about 5% viable. I normally don't like to say, oh, gee, look at all the dead cells, but in this case we're going to say, oh, gee, look at all the dead cells. And on the right, again, we can see in lane 2 where it says harvested media 2, 4, 6, 8, that's a number of days. This again is non-purified product, so even though we have 95% non-viable cells in this particular instance, we still have a fairly clean supernatant of our target protein being produced in CHOs. This is another difficult to express protein. It is a cytokine that is co-expressed with its receptor, so it's an interleukin receptor complex. It's highly glycosylated, 45% sugar. The only thing holding the two subunits together are the hydrophobic interaction between the receptor ligand affinity. And so we can see the productivity isn't great. It's around 50 micrograms per mil per day. We are able to produce gram quantities of this protein with our collaborator at NCI. And the important thing about this is to see that even after 137 days of continuous culture, there's no change in expression pattern, no change in glycosylation, no change in expression. So what we see is that a single harvest from a 2011 can equal 20 roller bottles per day. A single harvest from our larger cartridge can equal 200 roller bottles a day. So it's about 100 times higher concentration than what we see in versus flask or spinner culture. So hollow fiber bioreactors are, the method of choice for the expression of difficult to express proteins from mammalian expression systems.